Hello everyone, today I will show you how to find the numerical solution for the heat diffusion equation using backward time center space method. And the first thing that we need to know the parameters from the problems give us. We know the total length of the domain and the total time of the domain. We have four total lengths and one total times, and the diffusion coefficient is 0 divided by pi square. The time step size is 0.1, and spatial step size is 0.4. And the next, we need to set up the grid from the number of spatial intervals and the number of time intervals. We can define from the total length divided by spatial step size and the total times divided by time step size. That's we create the x start from 0 to L with an x plus 1, and t we also create from 0 to t with the nt plus 1. We can print the results in x and t and x and t to check the value from the that we define liquid site. And then we need to calculate lambda values from this equation. Lambda equals alpha times delta t divided by delta x squared. We can calculate from this equation, and we need to know what the value is, lambda, and we can print the values, and we will get the lambda is 0.253. And the next is the metric and apply conditions. We divided the domain into 11 positions and create uh, 11 times 11 zero metrics. The first column that we substitute the initial conditions into the functions psi pi x divided by 4 plus psi pi x divided by 2, while the other column remains still remains 0 for the future time step. And its position, we will get the value at the initial conditions at the time is 0. Okay, and the next we need to set up the backward time center space linear system metric. And we already know this equation, and we have to calculate the lambda from the past. We know the 0.255, and we substitute into the equation. We will get the 0 to 0.2533 and 1.5066 of its term, right? And then we at the time is 0.1 and equal 1. We will get this metric. It's called trigonometric, right? At the main diagonals, we will have the constant value from this equation, 1.5066, and the upper and lower diagonal is the main, it's the same values, is minus 0 to 533 at the same upper and lower diagonals. And we will have the 9 times 9 metric because of we start from I equal 1 to I equal 9, and we create the m equal nx minus 1 in its interior point, and the main diagonal we calculate from the equation 1 plus 2 lambda multiplied with the 1 matrix, and the off diagonals is the minus lambda 1 multiplied with 1 matrix also. And we need to combine all main diagonals and off diagonals, and we will get this metric. And the next, we need to calculate the temperatures at the time step of 0.1. We already have the metrics and initial conditions for its position. Using the inverse of the matrix, we can compute the temperature values, and this method this demonstrate a simple method to understand the solution, and we can extend it to the time stepping loop for further calculation. It's not simple, it's not complex like this. It show you to calculate to find the inverse values. Is a temperature at its position, and we need when we calculate inverse metric, right? We will get the temperature as its value of the time step of 0.1, and we will get the nice value, right? And from the 0.4 and 0.4.0, we will get the temperature values. And the next is we need to plot the solution in the position and temperature plane. And we need to calculate and visualize the temperature distribution along a lot at the specific time step. And the interior temperature values are computed from the metric solution, while the boundary temperature are set to zero, and the results are combined to the full arrays, which is then plot to show how the temperature vary along the spatial domain. For the next, we need to plot the temperatures distribution along a lot at the specific time step, and in the interior temperature point, we can see the graph at the t equals 0 to the t equal 1.0, increasing with the time step 0.1, and the temperature starting from high temperature to low temperatures, and the maximum temperature from the total the times is zeros, and the minimum temperature from the 1.0. And we plot the solution into the 3D planes. We will have the graph distribution like this, and time, space, position, and the temperatures. We will see that when the time increasing, the temperature will decrease from the high to lower temperatures, and the positions is the same, is a trend to increase like this. And this concludes the demonstration of the numerical solution for the heat diffusion equations using the backward time center space methods to find the temperatures. Thank you for your attention.